Okay. So today we'll be talking about for the customer-facing analytics for modern apps, right? Upserts, data freshness, joins, and more. Yeah, these are all pretty hardcore topics. But anyway, just a quick intro. I actually don't really think that's why I need to introduce myself again. But I'm Yingjun Wu and founder of RisingWave. And okay, so that's it. Okay, I just want to keep it short. Um, so yeah, start.
Hey,
Okay, yeah.
yeah, hey guys. I'm Sida Shen. I am a product manager at CelerData. I mainly work on a storage side of things, and also I host a lot of maybe too many webinars, and I write a lot of blogs. I also run our product marketing, and also I am a contributor to the Starbucks project. And before this whole Starbucks and OLAP database thing started, I was working in MLOps, so infrastructure for machine learning, right? And before that, I was a data scientist, doing like optimizations, operation research related stuff. So, hey, everybody, really excited for this discussion.
Yeah. Cool. And yeah, okay. So actually, I have already mentioned we were talking about a lot of things. Well, I mean, this will be pretty good technical, right? For and we will go through every single challenges like latency, freshness, consistency, joins, right? For everything. Okay. And if you have any questions, well, feel free to interrupt us because well, I don't really want to make it like a presentation, and we want to make it more like okay, uh right? For a fireside chat for that kind of style. Okay. Okay, so let's actually talk about what is customer facing analytics and what are
Yep,
requirements and challenges, right?
yep.
And okay.
Yeah, so in short, right, customer facing is the analytics that you serve to your customers, right? So it's directly serving your analytical workload, your SQL queries, to your end users, maybe in terms of just SQL query, that's less often, right? But mostly like an application, right, wrap around your underlying infrastructure or some kind of like a dashboard, right? An example can be an image on the right which is basically my YouTube studio interface, right? This is one of the YouTube video at our CelerData YouTube page, right? It shows the views and the watch time and how many subscribers it gains, right, in real time. And there are many more dashboard to this, right? A common characteristic of this kind of workload, how is that different from kind of like more like an internal analytics? Is it's extremely high stake because oftentimes customer facing analytics are the revenue driver for the business, for the company, right? For their, this is their competitive edge, right? So they want to
Mhm.
put every single thing that they have to get the best performance, to best latency, to serve all the customers that they have, right? And also to have, the best possible data freshness, right? Most up-to-date kind of data. Some example can be this is really widely used in B2B SaaS, right? B2B SaaS, you're serving your data, to your directly to your customer, something MarTech, right? And this is really big for fraud detection too, right? For in finance or in blockchain, we see a lot of customers doing these as well, right? In general, and these are external facing dashboards,
Mhm.
for all
Mhm.
app queries for your data.
Yeah, basically, I think for the a good way to summarize it that well, I believe that well, in most of the companies they actually have the internal dashboard, right? For and so in our case, well, I mean, as for database vendor, we actually have the I mean the let's say the community groups, right? Well, our AR groups, well, all these kind of dashboard, right? Well, and probably if, in finance team they actually have also some other dashboard. But for the dashboard we are talking about today is more user facing. Basically, who are the users? Probably like if you think about the Uber, right? Well, everyone take a Uber, and that's where there's a dashboard you can see, right? Well, how yeah, um, how many orders ever played, right? For because I
Yep.
typically use for Uber Eats and
Yep.
so some other logistics. I believe that's for logistics. Probably another big domain, right? So we actually have pretty um because well, they actually need to see, okay, where a certain kind is,
Yep.
right, well, and those kind of things. And the MarTech, well, to be honest, well, it's pretty big. Well, I really love this domain because well, they actually for advertisements, right? Every time you place advertisement, you actually want to track the ROI and all the what is called for the uh, per click, yeah, cost,
Yeah,
right? For those kind
yeah,
of
yeah,
things.
per click clock, cost per
Yeah,
click,
yeah,
and your CTR. And this is actually pretty big in like most
uh,
like social media platform, right? You have advertisers and you want to, and the advertisers need to see like how well their ads are performing in real time, right? So, they can make the best possible, reaction, right, to maximize their ROI. Something like Pinterest, they do something like that. And of course, for YouTube and for all kinds of social media platforms.
yeah, yeah, cool. And so what's the problem here? I know that there definitely are a lot of problems, right? So I think one of the challenge here is that we face, I mean, our at least our customers are facing definitely joins. Because Sida, can you discuss a little bit about why
Yep.
people need joins? Why not just like, okay, let's do a single table scan, something like that? Why
Yeah.
people need
So
joins? Yeah.
yeah. So I think a single table scan sounds good, right? Because joins is essentially one of the most expensive thing you can do in SQL query, right? But it actually does a lot more harm, right, than good, right? So let's start off, right? So the
Yeah.
relational
Actually,
database we're using like today was
mhm,
defined like back in like 1970s, right? You have multiple tables, right? You have some kind of key that connects to the table, and suddenly, like in the past decade, that has become not a best practice because a lot of the OLAP solutions and stream processing tools don't really have this relationship data in mind, right? When they build and design the system, joining multiple tables on the fly at query time, it was just not a consideration, right? So they didn't build this join operation support at all. Either they don't support it or they only allow single node join. Basically, you join that bottlenecks on one single node, right? Not uh, distributed join. So basically, it cannot take advantage of all of the nodes that you have,
mhm,
right? So the reason behind this is actually to do a distributed join, you need the ability to reshuffle the data, like at query time, right? So the nodes that you have can share the data that with other nodes, right? To do a big join, right? And most OLAP solutions that are available today for real-time analytics, for customers-facing analytics, are not really built that way, right? So it can only do very small join, like broadcast join, or like two very small table join, right? Or no join at all, right? Or make join so
mhm,
expensive that it's practically unusable, right? Or even they have shuffling, like something like Spark, right? It does have shuffling, but nobody really use that for real-time analytics. It's really not built for latency. It's built for like batch kind of workload, right? And
yeah. I
un
think Spark is totally different for thing. I
yeah,
mean, different
yeah.
from anything like no matter whether it's Starbucks, RisingWave, ClickHouse, whatever. It's totally different. Yeah, yeah.
Yeah, yeah, that is true.
Mhm,
So for real time, join just it's just not available, and this is a very
mhm.
obvious problem that we
Yeah.
see in this
Yeah,
field.
yeah. I think I mean we can definitely talk more about the in production use cases, right? Well, I can actually come up with one use case. Well, last slide we talked about market tech, right? Essentially, I noticed that well, many people actually want to join, let's say, event streams. Let's say, yeah, for yeah, in gaming domains, probably the telemetries, right? Or telemetry data, and they want to do enrichment. They probably want to join a table with let's say the customer customer data, customer information, right? Basic information, or signing up, right? And I'll probably even want to join something like, okay, their historical data, like, okay, how many games that a certain user have replayed, right? For this kind of like a historical data, they actually want to do this kind of joins. But I feel that for existing solutions, well, I mean, stream processing domain, or like yeah, Flink, right? Well, many people mention Flink. I mean, if you try to do multi-way joins or even two-way joins, well, if it's like two big window joins, then you will immediately find that way yeah, it will crash or probably it just got stuck.
Yeah.
But well, so and I know that well in overlap domains, well, there's ClickHouse, well, there are Pina, there are Drumi, yeah,
Druid.
Druid, right?
Yeah.
And probably there are many more. And do you think that's what they are good for joins or yeah,
Not really. I mean,
they haven't been optimized for
denormalization
joins,
has
right?
been like the
Mhm.
fake kind of, best practice in our field for the past, long enough I couldn't remember, right? Yeah.
Okay.
So, yeah, so join is just not there. I think there's an issue on the ClickHouse GitHub page that, shuffling service support and it's still there. Yeah. And after you
Okay.
build shuffling, you need optimizer too. You need like good query plan, to join multiple tables and do that fast enough, right? So that's just a whole different direction than what we envision this field would be.
Yeah. True. So yeah, I do hear people that well, I mean, I do not really work. I used to work in Redshift, okay, and
Yeah.
I have to say that's right. I mean, we definitely in Redshift definitely we optimize the job
Yeah.
a lot, but we know that as well. I mean, apart from Redshift, well, most of the vendors probably, I mean, smaller vendors, well, not investors too big. Smaller
Yeah.
vendors, they probably didn't really optimize for join. But I think well, in that case, well, Star Rock is definitely unique.
Yeah, I think
Yeah.
like not
Mhm.
having join is so challenging, right? So the thing is, like for denormalization, right? I'm okay with, building a few denormalizations on demand, right? To accelerate those like crazy workloads. That few customer that need like 100 milliseconds of latency. That makes sense. But building denormalization for all of your data is very harmful, right? So first it puts your data in a single view, right? So every time you try to update the schema, right, you have to track back to your original table, right? And all of the denormalized table that's associated with this table needs to be like backfilled 100%, right? Probably you just want to change something in your like a very small left table, right? But you end up moving like a trillion rows. And this is what we see a lot, with our customers. And this is actually the biggest challenge. And the second is really complicates your pipeline, right? And doing that in real time, I know stream processing has become a lot easier, right? Doing a few denormalization pipelines on demand is probably okay, but doing that for like all of your table is just,
Yeah.
it's still a big pipeline you have to manage there, right? And also it blows up, absolutely destroy your storage, right? 10 times is normally, in the ballpark of what we're saying, right? Let's
Yeah.
say like columnar format, compressed, you have like 10 gigs, 10 terabytes, right? Denormalized is normally like 100 terabytes plus, right? It really blows up your storage and actually slow down your query performance. We have that many columns, together, right?
Yeah,
So
yeah,
this
yeah.
is definitely a pretty harmful thing.
Yeah, so basically yeah, let me summarize a little bit. Well, I mean, let's say that your user has some Kafka stream data, right? And probably they also have some CDC data from the OLTP database, and they wanted to join. Uh, and essentially, I know that's why a lot of people actually also want to join data from the S3 or from Iceberg. Essentially, I believe that what I can see over the last 1 year is that's why, and actually many people actually started to join Iceberg data. Yeah, and the challenge here is that well, if you want to join all of this kind of data, right? Well, I mean, basically, anyways, you have to do joins. You have to do joins because well, you have different data sources and you want to do joins. The challenge here is that well, I mean, existing solutions are not very good. We're not very good at doing streaming joins. I mean, streaming joins is efficient because well, if you let's say that well, if you have some applications to directly serve a dashboard, right? And basically fixed pattern, right? But predefined queries, and you want to directly do the computation and store it like in a keyword store. Hold on a sec. Well, actually, RisingWave actually has the keyword store. So, yeah. But well, I know that well, some people also use something like Redis, right? Well, and you want to serve the dashboard. but you will immediately find that the streaming join is actually a bottleneck. And people will sometimes say that, okay, and actually in many cases, like, okay, I want to do ad hoc joins. How do you do that? And they use things like, yeah, I don't know, well, I mean, ClickHouse or some others, they will immediately find that, okay, this not optimized for the solutions, right? Well, optimized for joins, but they actually need to do this kind of joins so that they can show the result to the in the dashboard. So I
Yeah.
think that will be a huge challenge,
Yeah, that
right?
makes a lot of sense. So I actually have a question for you. So what do you see? Let's just imagine there is no rising wave, right?
Mhm.
For streaming. What do you see the biggest challenge is, for like some kind of like a stateful streaming joy, right?
Oh
What
wow,
is the biggest challenge today the
yeah,
user
like for
faces without rising wave?
okay, cool. So actually, the thing here that there are a couple of challenges. If you talk about ease of use, then essentially, some people I mean, okay, let's talk about performance first. And so if you want to use Flink, then many people will have the experience. If you have ever used Flink, you will know that there's a thing called RocksDB, which is
Yeah.
essentially the state management tool for the. I mean, they actually use RocksDB to manage their internal states. But the challenge here is that typically people want to do something like, okay, tell me doing a window drawing, right? Well, let me join the 7-day data with another, let's say, 1-day data, right? This is pretty
Yeah.
typical. And if you want
Yeah.
to do this kind of drawings, then you will immediately find that, okay, look, my RocksDB is not good enough because RocksDB is just like a single node disk-based database.
Yeah.
And it doesn't really work well. And it will immediately crash. And then people think about, okay, let me chop things up, right? Well, let's do partitioning, right?
Yeah.
But let's manually partition, right? Well, let's database sharding, right? Well, everyone says that, okay, look, MySQL isn't good enough. Let's do sharding. So same thing here in stream processing. People will say, okay, let's do sharding. But at the end of the day, you will find that essentially you have there's no optimal sharding solution, and also it's like a very time consuming because for everything you have have to be done manually, right? And
Yeah.
people will say,
Like,
okay, whether I can do something like, okay, Spark streaming, micro batch.
yeah.
The thing here that's
That's not
I mean,
streaming, right?
yeah, that's not
That's not
streaming.
streaming. That's not
Yeah,
incremental. It's not streaming, right?
yeah, yeah, yeah. That's right. Yeah.
I even got a shiver, when you said like state management. That's really something that's pretty painful, at least for myself.
That's right. Yeah, that's right. Basically, in our case, where it's like, okay, you don't need to do these kind of things. Well, you actually have to just write joins. Well, the magic here, that's well, okay, look, well, I don't really believe that's where there's any silver bullet in the
Yeah,
database domain.
yeah.
But what we have done is that we actually build our own state management storage, which is called Hammock, which is essentially
Hmm.
S3 as the primary storage. And the S3 is like super nice. If you have 7-day data, no worries. We'll just store everything in S3. That'd be good enough. Right. So we actually store everything for you. But
Yeah.
we actually have the caching layer, and to ensure that you are always perform at memory speed. And
Hmm.
that's about what streaming joins. Well, I mean, I can definitely talk more about I mean, the ease of use possible, but I mean, due to a time limit, well, let's just skip that
Yeah.
part
Let's move on.
for now. But for Thorox, well, I actually have more questions regarding yeah, let me check what it, actually, no, that's what we have
Yeah, we
yeah,
have the challenges laid out
yeah, yeah,
first.
yeah.
Yeah, I can go. I can go through those really fast.
Yeah, I want to talk about this slide. Well, can I just skip these two parts?
Yeah, yeah, yeah. Let's.
Okay,
Yeah, we
yeah,
can.
yeah.
We can come
Let's
back
talk
to it
about
if we
join
have the time.
first. Well, how to make
Yeah.
join fast when in StarRocks.
Yeah,
Uh,
so these two slides are just introduction for anybody that's not familiar with StarRocks, right? So it
mhm.
is a real-time data warehouse and a query engine, right? So this talk about like how we do real time. We can deliver substantial query at scale, right? Best in class performance for all of the real-time analytics, kind of like all app solutions out there. On the fly joins, right? So no denormalization pipelines required, right? So you can do those joins at query time, not like pre-join them like before, right? And also real time mutable data, you can do data upserts and get data freshness around like the 10-second around data freshness, right? So every data update every 10 seconds, and still you don't lose performance directly on our columnar storage, right? And it features a storage and compute separated architecture. Basically, you have your cloud object storage, and the data is persisted in your object storage. It's a caching layer that accelerate the query, right? So this is basically our Starrock's internal table format, right?
Yeah.
So all of the file format and table format that powers that real-time mutable data, right? And that's our own format. And
Yeah.
we can ditch our own storage engine, which I'm the PM for, sadly, and and
Yeah.
and
This
connect
part.
that with a kind of like a data lakehouse, right?
Yeah. This is the next update. Yeah.
Yeah, something like Apache Iceberg managed Parquet files, right? Can be your data lakehouse with the open catalog service, right? So you form like a lakehouse architecture, right? So you can, share data among like different compute engines and great for data governance, right? And we kind of ported all of the performance we had for data warehouse for real-time analytics to data lakehouse, right? Apparently, once we started kind of building that, right, we kind of figured out that Apache Iceberg and Delta Lake and Hudi, they behave just like a data warehouse. They're really similar to our own storage engine, right? So we could port like 95, 98% of our our performance, to the lakehouse, right? Supports all kinds of table file formats, right? And you have the same kind of performance and what drive, same feature that drives our really good performance, our MPP architecture. We can do in-memory data shuffling, right? That's great for low latency kind of drawing on the fly, right? We're C++ optimized, basically. We're written in C++ and we did vectorization, right? And that's great for query performance. Yeah, we do have the same caching framework that we built for storage and compute separated architecture, shared data architecture, and the same cache always still works, for lakehouse, right? So basically, get data warehouse like performance on the data lakehouse. That's including those like really extreme customer facing like use cases.
Yeah. Actually, the next slide is about RisingWave architecture. But well, actually, I want to double click on your architecture in terms of addressing
Yeah,
drawing issues. Well, can you describe something like in this slide?
yeah.
Yeah. So focus on joins. Well, let's say that's why I have 10 way joins. Well, join different 10 tables, right? So what's the challenge here?
Yeah,
And
so
uh,
the main thing, this is on the execution, execution layer, right?
sure.
So enable to perform a join, a distributed join,
Mm-hmm.
right? So join across different nodes, right? You need a shuffling service that shuffles your data at query time, right? So you do perform a shuffle join, right?
Shuffling
And
service is
yeah, a
yeah,
shuffling service.
basically
Like in
here, right?
Spark, you have that shuffling service,
And
right? But
yeah.
these are three kinds of basically architectures that we see, really high level architecture that we see
Mm-hmm.
in our industry right now. So first kind is scatter gather. It doesn't have that shuffling service. So when you do a join, your best bet is probably a broadcast join, right? You broadcast a smaller table to your biggest table, right? So uh it really bottlenecks on a single node. It's a very simple architecture that's bulletproof, right? It's stable and it's
Mm-hmm.
simple, but it's not really built for high cardinality aggregation, which is just a multi-phase aggregation that needs a shuffling in the middle. And it's not really useful for two big or multiple big tables joined together, where any of the tables not going to fit into one of your node, right? So this is scatter. You see some typical system that uses architecture are, let's say, ClickHouse, Druid, and Pinot just built their shuffling service, so they're not here anymore. So yeah, so this is the first kind, right? And then you
Mm-hmm.
have those, architecture that's really built for long running kind of like batch workloads, right? One example is Spark. Spark is not exactly like MapReduce. It's a more optimized version of that, but it's branched from like a MapReduce kind of architecture, right? So basically, it has a shuffling service, but each shuffle they persist every single of the intermediate result to disk, right? To do like task retry, if a 3 hour query or ETL job fails, right? So this is really great for long running ETL jobs, but their wait time between tasks because everything needs to touch disk, right? So this is really not that good for low latency, but this is built for like like long-running ETL kind of workloads, right?
Mm-hmm.
And lastly, you have like MPP, and some example can be like Trino and Starox, right? And even Impala, right? So basically, you're able to do in-memory data shuffling at query time, right? So between memory data shuffling, right? It really streamlines your pipeline execution, with absolutely zero wait time because memory is fast, right?
Mm-hmm.
It's great for like those like sub-second joins and aggregation kind of queries at scale, right? So if you do want to run low latency kind of join multi-table queries, MPP architecture is what's dominating all of the
Mm-hmm.
benchmarks and people's production system too.
Yeah, and actually, yeah, you talk about architecture, definitely. Probably just useful. Yeah, briefly discuss for the optimizer, right? So because I know that
Yeah,
I mean, like for the so let's say that there are 10 way joins, and the charge here is that some tables are probably so-called effect table and dimension table, right? So, and some
yeah,
tables are pretty big, and some tables are pretty small. And also, if you have a joins, you actually need to consider the selectivity, right? And
yeah,
all these kind of things need to be, yeah. I mean, if we just do, I mean, just join two tables or pairwise, so-called
yeah,
pairwise joins, the charge will be like, okay, probably the result could be super huge. And so I know that for Star Rocks will definitely optimize for the optimizer. And
yeah,
can you
yeah.
discuss something like that
Yeah,
about that? Yeah.
yeah, this is optimizer is
Hmm.
basically the heart of running like fast query, right? Execution layer, that
Yeah.
is kind of like a must have, but it's not really differentiated. You have it, you have it, you don't have it, you don't have it, right? You were written in C++, you written in Java like 5 times performance difference, right? 5 to 10 times. But query planning is where you really see a difference, right? It's like going from point A to point B, right? From going like to here to my office, like 10 miles. But you go the other way around the world, it's a lot further than 10 miles, right? So there are a million ways to execute a query. And the difference between a good query plan and a bad query plan is like it's like many magnitudes of difference, right? There are many things to consider, right? If you have multiple tables, how do you join those tables? Like which order do you join the tables, right? And which kind of join algorithm would you pick, on a single node, right? And what kind of distributed join strategy do you use, right? And
Hmm.
there is also a thing called a runtime filter. It's a little more detailed, but just show how much work, is put into something like this, right? You have a left table, you have a right table, and sometimes you can funnel the filter on one table to another, right? But sending the filter takes some cost, right? But sending the filter also give you some value. But which one is more expensive, right? So do you send the filter or do you not send the filter? This is called a runtime filter. Do we do a runtime filter or not, right? This is what the planner needs to take into consideration, right? And all of them, the state of the art approach right now for query planning is basically a cost-based optimization, right? So you compute your estimated cost for each one of the query plan that you potentially can run, right? And then you use kind of like a greedy algorithm to like pick the best one, right? And this is this state of the art, and probably the only way out
Hmm.
for us right now is a
Yeah.
cost-based approach, right?
Yeah.
And for Starbucks, we've been building this cost-based optimizer from scratch, from day one, right? It's been I think like 4 years now, right? It was very difficult. Thank God we're open source. We had the initial users that help us to iterate, this cost-based optimizer. I think this is probably the single biggest piece of asset, that's in our project right now, right? So
Yeah.
thank
Yeah.
you, Starbucks community. I do see
Yeah.
Starbucks users here.
Cool, cool, cool. Yeah, actually, I mean, I definitely fully understand how challenging it is to build a query optimizer because we're in yeah in Redshift we also I mean Redshift didn't really build an optimizer from scratch. For we actually used the Postgres optimizer, and the Postgres is super smart. I have to say super smart. We're super
Yeah.
smaller than most of the AI. But anyways, yeah, that would be that's but definitely that's very challenging. And because well, I mean,
Yeah,
Postgres is for single node, and if you want to do distributed, then it's also different storage, and you actually need to think more about for the all the other factors. So yeah,
yeah,
that's definitely it's not well. I mean, something that well any database well can build.
yeah,
Right. Well, I know that well, there are definitely all kinds of the OLAP databases, but if you ask me about okay, how much time these guys will build optimizers, I don't know. I mean, you probably can check, and
yeah,
probably can run some joins. I think the better way to, I mean, probably not do not check the code. Probably you can just run some joins and see the
yeah.
join ordering and see whether it makes sense. Right.
Yeah, you can see the plan. You can see the plan,
Oh, okay. Yeah, yeah, yeah,
yeah, you
yeah,
can
yeah.
you
It's
can just
plan, right?
check out the
Well, yeah,
plan and see the difference right there.
yeah, yeah.
It is really yeah,
Yeah. I
it
mean,
is a lot
that's
of
super
fun
cool. Yeah,
diving into the
definitely.
optimization.
Yeah,
It's a math problem and math is fun. So and
yeah.
we do have a question in the comment section. How does MPP ensure fail-safe queries when not fail doing in-memory data shuffling? So it in short it doesn't, right? So it's optimized for like different kind of things, right? If your query is like even too expensive to rerun, it's probably running in the minutes or at least in the hours, right? If you cannot afford to rerun that. So you're probably better off, going for something that's stage by stage, right? That's built for those like long running ETL workloads, right? So it doesn't, so you cannot really retry from like the middle of the query because it doesn't like cache any of the intermediate result, right? But most system like Starlux, what we do is to ensure that um the query gets retried and put back to the query queue if one of your node fails or in some sort of like a disaster, right? So
Sure.
it end up, you can still return result in a longer but still a reasonable amount of time. Right? I hope that address your question. So it's basically for different kinds of workloads. For what we run are mostly like sub 10 seconds, sub 5 seconds. For customer facing dashboards, normally like 1 to 2 seconds. So
Mhm.
failing a query is not the end of the world there.
Cool, cool, cool. Yeah, and well, actually, in RisingWave's case, so we are using very similar architecture. Definitely, I mean, stream processing. I mean, the challenging stream processing is kind of like different from the OLAP because well, in stream processing, the key concept is as well how you can. The key challenge here is that's well how you can manage the internal states, right?
Yeah.
And so in Starbucks, well, I mean, I think in this diagram is like you okay, actually previous one. So actually you actually have the storage in the basically Starbucks files in the cloud object store, basically S3, right? And
Yes.
similarly in RisingWave, we also do the same thing, or very similar thing. Basically, we actually maintain the internal states in S3,
Yeah.
or in object store. So I mean, I really love this architecture, and I believe that's where most of the modern databases are actually built on top of this architecture, right? And
Yeah.
but well, I mean, we have been building this architecture for 4 years. I think Starbucks guys will also spend years, probably 3 or 4 years, same, right? And
Yeah.
in building this architecture. I think what the chat people were ask us about, okay, so like well, this is a Hadoop-like architecture, right? Basically, it's just okay partition states. But the problem here that whenever you have let's say the hotkey or something like okay, let's do some yeah, basically it's really hard to balance your workload, right? And also the state itself, even if it's well balanced, the challenge here that's where the state can be, I mean, groaning, right? Will keep groaning. So and then your system can crash if you run something like yeah, probably Flink. You will find that okay, if you it's very complicated joins, then yeah, it will crash. But in writing of the case for anyways, for your data is actually stored, your internal state is actually stored in S3. So that's why you do not never need to worry about okay, well, what about the balance, right? Well, what about for the yeah, other memory issues? But for essentially, I mean, people definitely ask us about okay, what if like I mean, S3 is too expensive. I mean, in terms of the latency, and S3 is access. I
Yeah, I
mean,
was
if
just
you
gonna ask that.
yeah, yeah, yeah.
Thank you.
I mean, I think I think you guys probably did exactly the same thing. So, yeah, S3 latency is too high, and S3 access is not free, right? But S3 storage is cheap, 23 terabyte, $23
Cent.
per
Yeah.
terabyte, right?
Yeah.
It's cheap, but well, essentially access is super expensive. So what we did have done is that we actually have the disk cache, which, I mean, apart from the memory cache, everyone does that. We also have the disk cache, which allows you to leverage your local disk, no matter whether it's NVMe, SSD, or EBS, to basically to do a caching. So that's so it can eliminate 90% or even 95% of the object store access.
Yeah.
And I think in StarRocks, well, you actually do very similar thing, or probably
Yeah,
the
very
same thing,
similar
right?
thing.
So you,
So
because I noticed that, so you actually, I mean, I think for these two diagrams are pretty similar. Yeah. So yeah, you actually have the caching data.
yeah.
So is
Yeah.
it like automatic cache, or it's like, okay, I need to
Yes.
manually pick what I want to cache?
Yes, it is. It's very similar to what you have. So
Oh, okay,
basically,
cool.
a hierarchical automatic, a cache
Yeah.
that it does itself. It has a LRU, right? So it kicks out the unwanted or the hasn't been touched data, right? Right.
Yeah,
Yeah,
that's right. Yeah.
but it's tailored, for like customer facing like workload, right? Because customer facing is it's really intense, right? It's really low latency, right? The SLA requirements are just absolutely insane, unreal, right? So we built a few things on top of a classic, LRU memory disk based cache, right? So basically, we added a cache warm up, right? Before you start your service, you're able to like click and warm up the table that you want, right? And also to stabilize this performance, we did build something called like a segmented cache, right? So basically, you have a regular LRU segment, that you flush, right? And you have a protected segment, and that's automatic, right? Who goes into the protected and who doesn't, right? The reason why built that is to prevent one big query that flush all of the cache, out of all of the data, all of the hot data, every single piece of data out of the cache, right? To basically to stabilize your performance, right? To minimize the number of cache misses, in your production system. So
Yeah.
yeah, so yeah, short answer, we do have a cache, and cache is it's basically a must-have. When
Yeah,
you're using
definitely.
like a cloud object storage, like 100 millisecond latency just for the storage per scan is not really acceptable when the SLA is like half a second, right?
Yeah. Actually, also the for S3, I mean, it's I mean, yeah, I think probably a little bit different from you guys, but for essentially we actually, I mean, people really love to do the, I mean, point access, and not just, I mean, we also all storage is like row store, right? And people can just okay, search for a key, right? Well, and basically do a point access, and in the meanwhile, for the streaming joins, well, the pattern is also like, okay, I have the hash join and
Yeah,
I need to search for a key, right? In our case, so which means that in RisingWave's case, in many cases where it's like you actually have to, I mean, without this cache, without this kind of thing, you without the cache, you actually have to frequently access for the S3. So imagine that for every single access, well, I mean, for example, every single second you access 1,000 times,
yeah,
right? It
yeah.
definitely not accessible because not tolerable because well, for every single access will be, I don't know, 200 milliseconds. It's pretty standard.
Yeah,
Well, it's
yeah, 100 to
pretty,
2
yeah,
second,
200
200,
milliseconds is
yeah.
not a surprise for S3. Definitely not very surprise.
Yeah,
And
for every operation, it's not only like one S3, right? Seek. It's
yeah,
it's
okay,
it's many, right? So if
yeah,
everything touch S3,
that's right.
it's a year and a half query, right? Yeah,
Definitely,
it's very slow. It's
yeah, it's
great,
definitely
but
terrible.
you need a system to compromise, for it to right to compensate, the performance of S3, definitely.
For sure. Yeah, yeah, definitely cache is I mean it's pretty important for in
Yeah,
any I mean in any modern systems.
yeah,
Yeah, I mean S3 based systems. So anyway, sorry, I think I want to talk to something more yeah, probably at least for me it's more exciting, super exciting. That is performance. So yeah, let's look at for the StarRock's performance first. And
yeah.
can you yeah, describe a little bit about what table is and
Yeah.
yeah.
So thank you. So yeah, so this is basically SSB benchmark test. Starbucks, ClickHouse, and Apache Druid, right? So everything you see with a flat there is a variant of the SSB benchmark test. Basically, ClickHouse, the folks at ClickHouse, they took the SSB benchmark test, originally multi-table test, right? So they
Mm-hmm.
basically did a denormalization of the SSB schema, right? And
Oh, cool.
basically left um all of the aggregations there. So you still run the aggregation, but you don't run the joins on the fly, right? So
Mm-hmm.
that's the flat version of the test. And the multi-table, I'll see the right-hand side is the original SSB benchmark test with on-the-fly joins and the aggregations. So both, right? So basically, this is not a fair comparison, right? To compare with flat and multi-table because join is probably the most expensive thing you can do with a SQL query still, right? But flat query Starbucks is way faster than Apache Druid and is faster than ClickHouse. But the key thing here is Starbucks multi-table performance is actually better than Druid's single table performance. So you can basically, if you are a Druid user, Apache Druid user, right, you're doing a bunch of denormalizations, right? If your query pattern is similar to SSB and your data distribution, right? So you can basically ditch all of your denormalization pipeline and have your query faster, right? So that basically eliminates all of the rigidness we talked about, right? With data backfilling, with schema evolution becomes a lot quicker and easier, right? You ditch all of that kind of denormalization pipeline, that those Spark jobs that you're running, right?
Mm-hmm.
Right? You don't do that, or you do a lot less of that, right? And you save, 10 times of your storage back. You get like 10 times your storage back, right? And
Mm-hmm.
that is a great thing, right? And multi-table performance style is almost as fast as ClickHouse single table performance, and it's way faster than Druid's single table performance.
Yeah,
So
I
this is
actually
what they're
have a
talking
couple
about.
questions. Well, yeah, we only have 15 minutes left, but just let me ask one question. So in which case, I saw this. Well, definitely it's definitely amazing. Well, I mean, in which case will Star Rocks performs better than way better than ClickHouse, and in which case, well, its probably performance is kind of like similar.
Yes. So in terms of query performance, if you just run a raw aggregation on a lower cardinality column, so
Mm-hmm.
basically, that the performance is not that much different. It's faster or slower. It's just very like specific, right? Specific optimization that we do. But on an architectural wise, it's not that much of difference, right? You really start to see a difference when aggregation are done on a very high cardinality column, right? You need multi-phase aggregation, right? That needs shuffling, right? That multi-phase aggregation is a kind of optimization, it's only possible, right? When you can do shuffling, right? So on high cardinality, those hard cardinality aggregation, right? Stars is way faster,
Mm-hmm.
and also with joins. With joins, normally we see in production it's just Stars has a latency and ClickHouse just OMs because it cannot run that on their distributed, right? With multiple tables and big tables, right? Where
Mm-hmm.
broadcast joins just doesn't work, right? So yeah,
Yeah,
that's
yeah.
with ClickHouse.
Yeah, yeah, that's super cool. And also the other the other question is that well, can you expand? You mentioned the Druid. Well, I'm not an expert in Druid, but well, can you explain why Druid well the single table function is so bad well compared to I mean even compared to Starbucks for multi table performance?
Yeah, Java is slow, basically. Yeah, you need C++, you
Okay.
need vectorization.
Okay.
Vectorization is basically like we organize files in a column, right? The reason we do that is because like for OLAP query, it's always like column by column. You scan by column, right? So you organize a file by column, right? Vectorization is basically okay, in memory we do that in column too, right? And the reason why we use C++, we use SIMD. SIMD is basically for each instruction, right? You process multiple data. You see the thing here, like in column, right? In batch, right? So basically in OLAP, the more batch you run, the faster it's gonna go, right? And CMD is absolutely necessary, with any kind of aggregation or any kind of OLAP operation, right? And to do CMD, C++ is basically the easiest tool to do it, easiest language to do it in. In Java, they have that auto SIMD thing now, but it doesn't really work that well yet. Yeah, and also C++ is just overall like a faster language. So
Okay, cool. And actually, yeah, that's the Starbucks performance. So and so yeah, in RisingWave, I think well, I mean, we also have performance and definitely we compared with Flink and I mean I know that so we I mean RisingWave optimized performance a lot over the past few months as well. We actually always keep optimizing, but well, as you can see, I mean RisingWave performance is well. I mean this is next mark. Well, I mean if you have ever heard of like I mean have ever did research in stream processing, you know that this is a pretty standard benchmark for stream processing systems. And in our case, so it's like, okay, we also, you mentioned why you are better than the ClickHouse or why you are better than the others. Well, because we have joins and you have SIMD, right? So it's not in writing, you guys were writing C++, not in Java. And
yeah,
same story here. I have to say that it's just I don't know whether it's coincidence, but it's exactly the same thing here, as long as well, I mean, you have joins, RisingWave could perform way better. So if you can look, if you look at this diagram, right? Well, if you compare to Flink, if it's like stateless computation, I mean, okay, yeah, sure. Yeah, I mean, similar performance because it's probably just a filtering or some others, right? Well, I mean,
yeah,
you don't need to use for RisingWave. You don't need to use Flink. Probably using a Python, right? Well, right Python and it's done. But as long as we search, I mean, want to do something like okay, aggregation and joins, aggregation and top n, and right for all this like dist aggregation, you immediately find that for the huge performance gain compared to Flink. And especially if you want to do some fancy stuff like dynamic filtering, which is very cool. And I mean, and also the anti joints, semi joints, all these different joints, riding with
yeah,
it's way better. This is like okay in Flink, it probably not doesn't really work at all, but
yeah.
in writing wave it can do. And the writing wave is written in Rust, so so for sure. And yeah, that's yeah.
Is that a rustif or is that or is there optimizations or architectural decisions
I
like
mean,
difference?
so we actually started in C++. Well, a fun fact is that I only wrote C++. I personally only write C++.
Oh, okay.
And because yeah, if you check my background, it's like okay, yeah, basically C++ for yeah, guy. And but for essentially we so for Rust, well, I think for the decision was mainly because of the I mean the safety for
Oh,
the
okay. Yeah.
yeah right. Well, I think the in terms of performance, well, it's very similar to C++.
It's memory
Uh,
safe. Yes.
yeah, and but I think the limitation. I think probably we developed started working on this project 4 year, 5 year, almost 5 years ago. And but for the at that time, I think the limitation of Rust was that well, the library isn't good enough.
Yeah.
But if you check today, it's like okay, every single company, big companies, right? Well, no matter whether it's Facebook, Google, I mean, they
Yeah.
always claim that's where they want to have Rust. Well, I also know that's why. I mean, for Linux, where they also implement
Yeah.
Rust, right?
Yeah. It's a
Um,
Rust implementation for everything. It's Rust for Iceberg, Rust for Delta, Rust for
oh yeah, we contribute to
yeah.
the Iceberg Rust. So
Yeah.
yeah, we can actually mention a little bit. I'm not sure whether we have slides covering the. Okay, we do still have more slides. So I'm not sure whether we have a slide covering the iceberg thing. But anyways, well, can you spend probably 2 minutes discussing the mutable data? Because well, I mean, I think well for I can just give a pretty quick intro. Okay, so mutable data means that well you the data have changes, right? Let's say that we have a MySQL CDC, Postgres CDC, MongoDB CDC. Those are changes, right? Changes are always bad for the. It's not bad, well, but bad for the systems because
Yeah.
you actually have to do compaction in order to
Yeah.
yeah compact different nodes, right? Well, for writing wave, we have already started. I mean, we from day one we started for the CDC and we
Yeah.
do all these kind of compactions. And how about Starbucks?
So for like Upserts, it's a surprisingly if you're a user, it's probably surprising, like how it's difficult to like update a role, right? But it's pretty difficult for OLAP system because we organize the files in a columnar format, right? So if you just want to change that one file, you need to unpack that big ass file and basically rewrite the file, right? Right. Most of the file formats that we use, are immutable. So right. So upsert is actually a very surprisingly difficult thing to do, right? But the industry right now, the common thing, for data upserts in real time, right? We use something called a merge on read, right? So you write, and there's a background job that merge all of the changes, right? And and then you read, right? But the challenge is most merge on read implementation without any kind of like record level index is too slow, right? So the compaction job cannot really catch up, or it's taking too much resource that's gonna affect your query performance, right? So let's say something like even Apache Iceberg, merge on read implementation and a ClickHouse merge on read implementation, you want something like 5 minutes of data freshness as max, right? It really depends on the amount of data that you have, right? But like 5 minutes is the most you can do, right? But what we implemented here, delete and insert strategy, right? So you do a mark delete during ingestion, right? And then you basically filter the mark deletes at query time. This is quite similar, right, to most of the implementations. But here is we do have a record level index, a primary key index to accelerate the mark delete process, right? So the mark delete is resolved basically at
Mhm.
ingestion time. So there's like no merge operation at the end. So you get the best possible performance. There's no compaction job that interfere, with what you're trying to query, right? So basically you can do second level data upserts, directly on your columnar storage without a row. With a row index, but without a row store, right? With a record level store, right? So you need like fraction of the storage, even better query performance when compared to, other solutions that similar solution that has like maintain a full row store and a columnar store. And you can
Yeah.
enable real-time mutable data, real-time analytics to all of your data, right? Including mutable
Mhm.
data, right?
Yeah. Okay, we actually only have 3 minutes left, but for let's just spend 1 minute, just 1 minute, we're
Yeah.
discussing a little bit about and then we can discuss something about the customer stories. Okay, and
Yeah.
what's the what's your take on AI?
Yeah. Yeah, my take on AI. So, yeah, in our field, I just talk to users and learn from them, right?
Mhm.
AI agents is coming, right? It's not only coming, it's here. Yeah, a lot of our users, they're building agents right now, right? And AI agents, their requirements are like actually they're like customer facing, but it's like AI like scale, right? So you get a lot more concurrency, right, than you can ever imagine, right? You have to be able to serve, those like I don't know, got many of AI agents, without performance degradation, right? And you need that sub-second, still that kind of latency, right? For humans, probably, is you don't wait, right? But AI agents are a lot faster decision makers than human, right? So this is gonna be an even bigger bottleneck if your query performance slow. And most importantly, I think you need AI ready architecture, right? So you want your agents to have every single one of your agents to have a view of all of the data that you have, in your organization, right? There cannot be data silo, right? So storing everything in the open format, right? Governed by a like an open table format, something like Apache Iceberg, is really vital, for like talking about like AI agents in the future, right? And also, for engine itself, it needs to be like self-optimizing, right? It needs to do everything by itself. AI agents writes crazy queries, right? And we have to have ways uh, to automatically tune performance, automatically separate or isolate workloads, right?
Mhm.
To deal with large stupid queries that the AI might produce, right?
Yeah. Yeah.
This is all built for like future AI-driven workloads.
Yeah.
Actually, not that much future now. It's actually today's AI
Uh,
agents kind of workload.
Yeah, so okay, so for the last minute, I definitely want to discuss something about the customer successful stories. Well, I mean, we
Yes.
also have another. I mean, the previous slides I skipped the Airbnb part. Well, but for I mean, at the very beginning of the conversation, we talked about the iceberg, right? Well, yeah, essentially, RisingWave and Starbucks were pretty. Yeah, we have pretty good successful stories for in many companies. Well, and I think I believe that's definitely yeah we collaborate with some SMBs or mid market as well. But for I believe that's the most proud of the deal we customer, right? Well, we supported actually basically a pretty big trillion dollar company, right? Well, and they actually moved from Snowflake to Iceberg, and then they adopted for the Starrocks for query engine and RisingWave for the ingestions. So tell me something about for the Iceberg. Is Starrocks very good at for let's say joining multiple petabytes of data? Is it for what you can do in
Yeah,
Starrocks?
I mean, yeah, like scanning petabytes of data, it's scanning against the data lakehouse or iceberg, table with petabytes data. Okay, but actually scanning, but I don't know, but yeah, so people use us for the biggest kind of workloads. I mean, we see Starbucks users having, some of the biggest iceberg clusters in the world, right? Or not iceberg cluster, but iceberg like scale in the world, right? Like Tencent games, right? Petabytes, and we have red note petabytes, and we have all sorts of biggest some of the biggest scale in the world for Apache Iceberg, right? And
Yeah.
we also bring that same kind of performance, from a data warehouse, proprietary data warehouse that better than ClickHouse, faster than ClickHouse performance, on Apache
Yeah,
Iceberg. So
that's right.
with
Yeah.
joins,
Yeah. So basically, I think what I mean regarding a Snowflake. Well, I mean, the challenge here that for Snowflake is great, but I mean in terms of the ease of use. But if you talk about the cost, that's I mean think about it. But fine, yeah, you can make your own decision, right? Well, I mean whether to use Snowflake or not. But well, I mean, addition to that, well, the another limitation is about well, it's yeah low latency serving, right? Well, that's
yeah.
the other limitation of Snowflake. So I think where that's where Starrocks can shine, right? Okay, we are running out of time, definitely, and but well, I mean, it's I actually started yeah at the very beginning I told you that we cannot go through every single slide, but definitely there are a lot of the content is super rich, and we skipped a lot of details, but yeah, if anyone is interested, yeah, just ping us, and the best way to reach out to us is to join our Slack committee, right? For in RisingWave, it's risingwave.com Slack or join Starrocks Slack committee. We can actually, I mean, you can join either and we can refer you to the others. And for the clouds, Rising Cloud is risingwave.cloud and the CelerData cloud is cloud.celerData.com. Okay. All right.
Any
Okay,
question?
that's all right. And we're running on time.
Yep.
So yeah, it's really nice having chat with you. Okay, there's one question. Okay, so okay, just one question. Yeah. So um,
I think I addressed that already. Mid chat and
okay,
PP fail safe. Yeah,
okay,
I think
okay,
that's all the question we have now.
okay.
Do you have
All
any more
right.
questions? I'll give you like 5 more seconds.
Okay. So,
No?
anyways,
Okay.
I think I'll
Fine.
probably just post in the channel and I
Yep.
mean in a Slack committee or wherever. Yeah, you can always reach out to us. Okay.
Yep.
All right. All right.
Sure. Thank
Thank
you.
you,
Thank you, Yingjun.
everyone.
Thank you.
Thanks. Yes, super
Thank you.
informative.
Appreciate that. That was
And
a lot of fun.
yeah. All
Thank
right.
you.
Thank you. Yeah.
Bye.
Bye.